Hey everybody, today we are talking about bonding, which is pretty exciting because we're going to be using a lot of the stuff that we learned in atomic structure and the periodic table to understand why bonding occurs between atoms, and specifically how we can predict what bonds are going to occur and how many atoms of each type we're going to need to make a particular compound or molecule. So we're going to, very briefly want to review some of the things that are important from last week. With our periodic trends, we know that as we get across and up the periodic table towards fluorine, those atoms are becoming more electronegative. That means that they're more likely to steal other atoms' electrons and hold their own very tightly. They're small and feisty. They like to steal electrons. And down here with francium, francium is that largest atomic radius on the periodic table, largest atom on the periodic table, and its singular valence electron, because it's in this first group, the alkali metals, its singular electron is barely holding on. It has many, many layers of shells of electrons that are blocking the attraction of the nucleus, and very, very large atom with only one valence electron barely attached. Again, one other thing that's going to be important over and over in bonding is figuring out how many bonds something's going to make. So to know that, we have to know how many valence electrons the atom has. And we saw that this first column, they all have one valence electron. And that this second column, they all have two valence electrons. And then we skip the transition metals. Everything in boron's column has 3 valence electrons. Everything in carbon's has 4. Everything in nitrogen's group has 15. Everything in oxygen's group has 6. I said 15, I'm sorry. Everything in nitrogen's group has 5. Everything in oxygen's group has 6. Everything in the halogens, this pink group, has 7. And then here in the noble gases, they mostly have 8. The one exception is helium, which has 2, and that fills its shell. And we know, that the alkali metals are very reactive, and the halogens are very reactive, and that the noble gases are not reactive at all. They kind of are just chilling. So where this is important is that in bonding, we follow a lot of times something called the octet rule. The octet rule is the rule that states that all atoms are trying to get a full outer shell, a full valence shell of electrons when they bond. That is why they are bonding. That is kind of the goal in the bonding process. And so in a way, hopefully that'll make sense, because the alkali metals, we know they're very reactive. Well, they're only one away from having a full outer shell, right? They could lose this electron and fall back on the previous shell in the Bohr model and be full, right? Like, they're very close. Similarly, the halogens, they're also only one away. They just need to steal one to get to 8. So we're going to be working with this more later this week, but starting to kind of pay attention to, like, hey, if this only has 2 valence electrons and it's less electronegative because it's on the left side of the table, it's not stealing anything, it's pretty big, they're not attached very well, there are only 2 of them. When it bonds, this group of the alkaline earth metals is going to lose its 2 electrons to any nonmetal that's strong enough to take them, right? A couple things I want to mention on this. For almost all atoms, we are trying to get to 8, but just like any model is not perfect, any rule has exceptions, and in this case, hydrogen and helium are exceptions. Exceptions because hydrogen wants to make 1 bond to get its shell of 2, to get to that noble configuration, and helium doesn't react really at all as a noble gas. The other section that has exceptions is the transition metals, which we'll talk about a little bit more later on. So there are 3 types of bonding. The first is ionic bonding. Ionic bonds occur between a metal and a nonmetal, and this is a apt time to remind you all that the stair step on the periodic table that I'm tracing right now with the cursor, that separates the metals from the nonmetals, right? So if we take one of these and we put it with one of those, metal and a nonmetal makes what's called an ionic bond. A lot of times we'll also call that a salt. So the nonmetal is the more electronegative atom, which we know from our periodic trends. It's going to steal the electrons from the metal. Remember that on our green summary sheet about a week ago, we said, if we change the number of protons, we make a new element. And if we change the number of neutrons, we make an isotope. Well, if you change the number of electrons, you create a charged atom. And a charged atom is called an ion. But that's not complicated enough. There is a cation and there's an anion. So the atom that loses its electron, possibly plural, possible, like maybe it lost 2, maybe it lost 3, somewhere in here, possibly 4. So a metal that's lost its electrons is going to be positively charged, all right? It's going to be positively charged because it is losing that negative charge. When we have a positively charged anion, we call that a cation. So if we look down here at this drawing with sodium and chlorine, we can see that sodium in the reaction where they're bonding loses its electron to chlorine. That makes sodium a cation. It lost 1 electron, and now it has a charge of +1. Alternatively, chlorine, as a nonmetal, on the right side of the periodic table, where it's more electronegative, and it's stolen electrons. It's gained extra electrons. It's gained 1 extra electron, become negatively charged, and is called an anion when that happens. So here, chlorine stole the electron, became a -1 anion, and we have a cation and an anion forming an ionic bond. We have a full positive charge on sodium, a full negative charge on chlorine. They're going to be very strongly attracted to each other. It doesn't always have to be +1 and -1, but the number of electrons being moved will always be indicated with a number next to the charge sign. So it'll say 2+ or +2 if it was losing 2 electrons or gaining 2 electrons or vice versa, etc. Last thing I want to say about that, if you look at these drawings right here, ionic bonds form crystals. There are these ions form a lattice, and if we could peel into the middle of this square or cube, we would see that every cation is surrounded on all sides by the anions, and all those anions are surrounded by all sides on a cation. And they're all held together by this attraction to each other that's coming, just like we saw last week with the static electricity, is this charge of attraction where there's a full positive and a full negative. Okay, so if we take one of the metals and one of the nonmetals, we put them together, the difference in electronegativity is sufficient enough for the nonmetal to steal it. We get ions, and that makes an ionic bond. What if we take 2 nonmetals? Well, if we take 2 nonmetals, that makes up a covalent bond. And in a covalent bond, the electrons are being shared between the atoms. So it kind of looks like these drawings over here when we have one line between 2 atoms. That's indicating that there is a pair, 2 electrons, big shared between this hydrogen and oxygen atom. And over here, this hydrogen is sharing a pair with oxygen. So if we think about that, when you have a covalent bond, the electrons count for both atoms. Like they're sharing them, so they both get the count. So hydrogen here, it's got one that it's contributing and one that it's sharing, and so total it has 2. And that's what hydrogen needs to get a full outer shell. And oxygen, it has 2 and 4 that it owns, that are lone pairs that are just on the oxygen. And it's also sharing 2 with this hydrogen, so that brings it to 6, and 2 with this hydrogen, so that also brings it up 2 and makes it 8. So oxygen has an octet. So you can have single bonds, you can also have double or triple bonds, which you may have seen in your molecule last semester. A double or a triple bond is going to be a little bit stronger, a little bit shorter. and it changes its three-dimensional shape in space a good bit. Sometimes people like to say, oh, ionic bonds are stronger, or oh, covalent bonds are stronger, but the reality is it's kind of depending on the situation that it's in. You know, ionic bonds can go a little bit higher, I believe, than covalent bonds, and from what I've seen in strength, but there's such a wide range, and it really depends on which atoms are participating in the bond in either case. So you all may remember from last semester that in water, oxygen's kind of hogging the bonds, the electrons that are being shared in the bond. And so it has a partial negative on it, and it makes it polar. But oxygen hasn't fully taken it from hydrogen, right? Like hydrogen's barely hanging on there, but it is hanging on still. So there's not a full charge like we saw up here where it says plus and minus. There's like a partial region of higher electron density. So because all the nonmetals are packed into this region, they're all about this. They're closer in electronegativity, and so that's why neither is strong enough to pull it away from the other. The last type of bond is a metallic bond, and metallic bonds occur between two metals, as you might imagine. We're not going to talk about these quite as much, but I want to mention them because they're very cool and interesting as well. But they break the octet rule a lot, and so that makes it a little harder you have to know like a little bit more to see what's probably going to happen when you're having metals bonding. So all of the metals we know they're relatively large, especially as we head this way, and they're not very electronegative. They don't hold on to their electrons very tightly. A lot of times they have somewhere between 1 and 4 that they're going to be trying to get rid of. And so what happens is we have this thing that's called a sea of electrons, where the electrons are kind of just distributed, not really at random, but very loosely amongst the atoms. And that is why, with the low electric negativity and the fact that they're delocalized, electricity will flow well through a metal, is because they can kind of pass that current down the line. So once you're done with your notes here, what you're going to be doing is taking the worksheet that I'm handing out, and you're going to look at an example that's going to say, hey, you're taking beryllium and you're combining it with sulfur. What kind of bond is that? Well, I've got a metal, got a non-metal, so that's going to be ionic. All right, and you're taking phosphorus and oxygen, and is that going to be, ionic or covalent? And you're just practicing identifying and using that vocabulary. Hey, an ionic bond is between a metal and a nonmetal, and a covalent bond is between two nonmetals, and that's what that worksheet's about. So to recap, the octet rule, everything's trying to get to a full outer shell, generally to having 8 electrons. Metals are not very electronegative. They don't hold on to their electrons very tightly. They're more likely to pass those electrons off. Nonmetals hold on tighter and are more electronegative, so they're more likely to try and steal. When we take a metal and a nonmetal, the difference in size and electronegativity is sufficient enough that we get an ionic bond, where the metal loses electrons and becomes positively charged as a cation, and these nonmetals become negatively charged by stealing electrons, anions, and that is an ionic bond because we have these two charged ions next to each other. And the other type of bond that we're going to focus with, that's the bond that makes up everything that not everything, but many of the things that we eat and drink and the things that make up our bodies. We take 2 of the nonmetals and put them together. They all have similar electronegativity being packed into this area, and so they share their bonds, and we show that those bonds are being shared with the line between the 2 atoms. Hopefully this is helpful and interesting, and thank you all for your attention, and good luck on the worksheet.